Thank you. Good morning, everyone, and welcome back. Today we are going to finish up everything else there is to know about hyperbolic 3 manifolds in 1 hour. It's going to be great, but fasten your seatbelts. Okay, so I just put up, this definition was from the end last time about normal surfaces. I put it up in case you want to refer to it. You may need to refer to it, and since it involves some pieces, it will be there for you to see. So I'm not going to talk about that first thing. The other thing I guess we ended with last time was, a new tool that we're talking about is Thurston's hyperbolization theorem, which said that either a 3 manifold with a torus boundary, it's either hyperbolic or it admits an essential torus, annulus, sphere, or disk. Okay, so we're going to be looking at 3 manifolds that have some sort of a polyhedral decomposition, and we're going to be trying to rule out spheres, tori, annuli, and disks. So that's the goal for the first part of what we're going to do today. So let me tell you of a type of 3 manifold which has enough structure in order to run this program through. So this is called manifolds with an angle structure. And sometimes this is called a strict angle structure. So, okay, so the definition is, suppose that you have a decomposition of your manifold into ideal tetrahedra. Okay, well, in this case, a strict angle structure for the manifold M is a collection of angles. So you have a collection of interior dihedral angles one for each edge of each tetrahedron. And they need to satisfy 3, possibly 4 properties. Okay, 4 properties. Property 0, opposite edges of a tetrahedron have the same angle. Okay, so here's my ideal tetrahedron, and I'm going to be labeling each edge by some angle. So if I label this edge alpha, then this edge over here is also labeled alpha. Okay. Number 2, or number 1, the angles lie in the range 0 to pi. So these are going to be, these are assigning dihedral angles to an ideal tetrahedron. So as long as the angles are between 0 and pi, the tetrahedron will not be flat. If it's angle 0, you got a flat tetrahedron. If there's one that's angle pi, you have a flat tetrahedron. So we're mimicking some hyperbolic geometry here, but what we're doing is not quite going to be as strong as hyperbolic geometry. You have that the sum of angles around an ideal vertex is always pi. Ideal vertex of a tetrahedron is pi. Okay, so here if I label this edge beta and this edge gamma, what this is telling me here is that the sum of these 3, alpha plus beta plus gamma, is equal to pi. Okay, so that's what you would have if you have a hyperbolic structure on this tetrahedron. And then finally, the last condition is in an edge class. So all of the edges that are identified together to form the 3 manifold, you need the sum of angles around this edge class to be 2 pi. Sum of angles around an edge class is 2 pi. Okay, so the picture is, if I've got these tetrahedra all glued, then this angle here is 2 pi. Okay, and that's it. So notice, this is weaker than a hyperbolic structure. So last time we were looking at gluing and completeness equations. Let me bring that down where I can reach it. I actually want this one first. Okay, so observe. So this is like taking our gluing equations. We had these complex numbers and we were multiplying them all together and getting 1. This is like just stripping the angle information off of a complex number. So forget how big the number is, forget its magnitude, just think about its angle. And if it satisfies the gluing equations, then its angle will satisfy these properties. But there's no restriction on the magnitudes of these. So observe, this is weaker than a hyperbolic structure. So item number 3 in particular is analogous. Analogous. It's a hard word to spell on the board. Analogous to the gluing equations. But it allows things like shearing. Okay, so the following would be a legal angle structure, although that's not giving you a legal hyperbolic structure. Okay, and also there's no analog over here to the completeness equations. So we can ignore the completeness equations. Okay, so a manifold that admits a hyperbolic triangulation, so if you have a structure that satisfies the gluing equations, then it will also have an angle structure, just by taking that complete structure and looking at its angles, but it actually will have lots and lots and lots of angle structures. So whereas there's a unique hyperbolic structure, if there's an angle structure, there are many angle structures. Okay, question so far? All right, so this is not strong enough to give you something hyperbolic a priori, but it actually is giving you significant geometric information. So we're going to encode some of this by looking at what is called combinatorial area. Okay, so definition. So let's suppose that M has an angle structure, or a strict angle structure. Okay, so why the word strict? Some people allow angle structures to also have flat tetrahedra, so to allow 0 and pi, but we're not going to do that. So I'm probably going to drop the word strict from the rest of my lecture, but if you have worked with, if you have called these things strict angle structures, that's what I'm talking about. Okay, so let's suppose that M has an angle structure, and let's let D be a normal disk. Whose boundary meets meeting edges with angles alpha 1 through alpha n. Okay, so that is, my normal disk is embedded in a truncated ideal polyhedron in this case. And so it's going to meet some number of edges that have angles on them. It's also going to meet these boundary faces and edges again next to the boundary faces. And so those So let's give that a name too. So let's let the boundary of D intersect the boundary of M. So it meets this number of boundary faces. Okay, so recall the boundary faces came from the truncation. So then the combinatorial area of D is defined to be okay, first thing you do is you sum the exterior angles met by D. You subtract 2 pi because it's a disk, and you add back pi times the number of boundary faces. Okay? And an exercise, if D is a totally geodesic hyperbolic polygon, and it's meeting all of the edges at right angles, then this is actually the hyperbolic area of that polygon. Okay, so maybe I'll write that over here. Exercise. This is the actual hyperbolic area of a totally geodesic polygon. Okay. And then finally, we define, so if you have a normal surface, normal surface embedded in M, then the combinatorial area of S is just to be defined, it's defined as the sum of the combinatorial area of its normal disk components. Okay, so DI normal disks. Okay? Okay, let me give a couple of examples. So, all right, so truncated tetrahedron here with angles, let's say alpha, beta, beta, and gamma. Then here's a normal disk here, and the area of this disk D, well, from the formula, I sum pi minus alpha, pi minus beta, pi minus gamma. Okay, and then I subtract off 2 pi because it is a disk. And then I add on pi times the number of times that this meets boundary faces. Well, it doesn't meet any boundary faces. No boundary faces. Okay, so this simplifies to be 3 pi minus 2 pi minus alpha minus beta minus gamma. So that is pi minus alpha plus beta plus gamma, which simplifies even further. Does anybody see what that is? That is 0 because alpha plus beta plus gamma was required to be pi. That's item number 3 in the definition of an angle structure. So this is 0. Okay. So there is one example of a normal disk with combinatorial area. Let's do one more. Let me pick so let's do this one. So it runs over this bit of boundary face, this bit of boundary face, and then connects up in the back, like so. Okay, so let's call that, maybe let's call that E. Okay, so let me give myself a little space. So the area of E, okay, so first of all, notice that this doesn't meet any edges with angles. So I get 0 from my sum of the exterior angles. I subtract off 2 pi, and then I add back pi times 2, because this meets exactly 2 boundary faces. And so this also has combinatorial area 0. Okay? Where are we? So I claim, so these are actually 2 important examples. So if D is a normal disk in an angled structure, angle, I didn't put a D on it. Then I claim that the combinatorial area is always equal to 0. And it equals 0 if and only if D is one of these 2 examples. Okay, so let's, these actually have names. Let me name them, maybe over here. So the D up here, this disk, this is called a vertex triangle, because it's just parallel to a vertex. And this one down here is sometimes called a boundary bigone. Although I don't know if I like that terminology, but it's got 2 sides on regular faces. I think that's where the bi comes from. Okay, so this is not too hard to prove. Let's go over it really quickly. Okay, so first notice if you meet your boundary at least twice, then where did the formula go? Here. Here's the formula. If you meet the boundary at least twice, then you're going to be adding something positive to negative 2 pi to something that's at least 2 pi. So it's going to be positive, or at least non-negative in this case. Okay, so then it's greater than or equal to 0, and notice it will be equal 0 only if you meet the boundary exactly 2 times, and you don't add on anything extra that's positive. So that means, and there are no intersections with interior edges. Okay, and this implies that you're a boundary bigone. So there's one case. Okay, another case. Let's suppose that you meet a boundary face exactly once. Now we use the fact that this is normal. Okay, so let me draw bits of tetrahedron. So let's suppose I meet this boundary face. Then I get these arcs of the boundary of D that have to run somewhere. They cannot run, so not here and not here. For this guy, by definition of normal, this is item number 3. You can't run from a boundary face to an adjacent boundary edge, okay? So that means, so boundary of D cannot meet an adjacent edge so it must run to opposite edges. So that means it's got to go here, and it's got to go here, and these are never opposite edges. So, okay, so I'm overusing the word opposite. It's meaning the 2 edges, okay, meets edges, meets those edges that cannot be opposite in the tetrahedron. Okay, so this means my area is at least, let's say this is alpha, this is beta. So we get pi minus alpha, pi minus beta, minus 2 pi plus 1 pi, which is, what? We get pi minus alpha minus beta, and this is gamma. This is the 3rd angle of the tetrahedron. And so this is going to be strictly positive by definition of an angle structure. Okay, so that's what happens in this case. And then finally, there's one more case. So now we're not going to meet any of the truncated faces. So we're only meeting the edges. Then in this case, there are only 2 options for D. It's either a triangle, a vertex triangle, or a quad. So let me circle that in red. Make that an exercise. This is classical normal surface theory. This is what Knaser was doing. So the claim is if you never meet a vertex, then you are either a triangle or a quad. We've already dealt with the vertex triangle case. We know that its area is 0. In the case of a quad, then you are meeting, so what does a quad look like? Something like this. It will actually meet 2 edges labeled one thing, 2 edges labeled another thing, and no edges labeled the 3rd thing. And so the area in this case is 2 pi minus alpha plus 2 pi minus beta. And this is going to be positive. Okay, so that's it. So we're done. Oh, minus 2 pi, sorry. This is very positive, but it's wrong. This is more positive, or less positive, but still positive, and that's correct. Yeah, thank you. Okay, did I miss anything else? All right. Okay, so we need one more tool. So all of this is kind of approximating. This is combinatorial area. It's not real area. I'm making up this notion of area. But it turns out to be quite strong geometrically. So you can, for example, prove without too much work the Gauss-Bonnet theorem. Okay, and the proof here The proof is not hard. It's combinatorics. You look at Euler characteristic of this thing. So combinatorics. And so I'm going to leave it as an exercise. It's a little bit longer than I want to spend time on right now, but it's not too long that you can't do it on your own. Either you can do it as an exercise or you can also look it up. It's in, this is all I should say. This is all in a paper by Mark Lackenby, Word Hyperbolic Dane Surgery. You can find it as well in somewhere in my very large book, chapter 8. Okay. Okay, so now, all right, so I told you that an angled structure isn't strong enough to give you hyperbolic geometry, and now I have to retract that because in fact it is. So Casson was the first one to show this. At least this is attributed to Casson. He never wrote it down. Mark wrote it down in 2000. And the result is if M admits an angled structure, then M is hyperbolic. Okay, so somehow this is enough to tell you that the manifold is hyperbolic. A few caveats. So I'm going to prove this by contradiction. So I'm going to show you that there's no way it cannot be hyperbolic. But what this is not going to give me is it's not going to find for me the hyperbolic structure. It's just going to tell me that a hyperbolic structure is out there. It's not going to tell me that the angle structure that you give to me has anything to do with the hyperbolic structure. It's not going to tell me that the angle structure you give to me is complete or satisfies gluing equations or anything. It just tells me that somewhere out there in the world there is a hyperbolic structure. Okay. Yes?
Could the edges from your original triangulation be knotted in the structure? Or?
Could the edges from the original triangulation be knotted in the structure? There's no reason that they wouldn't necessarily be, I think. Yeah, so this, the triangulation that you pick to get your angle structure may not be a good triangulation at all. Yeah, maybe I don't know of examples where they're knotted, but I don't think there's any way to rule that out a priori. Yeah. It's actually hard to find examples of angle structures that aren't the right triangulation somehow. But they exist. They do. Okay, so let's go through the proof of this. So the proof is just pulled together by assembling all of these pieces that are all on the board, everything that I need except for I didn't write down the hyperbolization theorem of Thurston. So let's start with that. So let's suppose that it's not hyperbolic. So then Thurston's hyperbolization theorem tells me that there exists either an essential sphere, disk, torus, or annulus. Okay, let's give it a name. Annulus S. By things that we talked about last time, I guess that are also not on the board, you can isotope this to be into normal form. Or, sorry, you can take S to be in normal form.
So are you assuming something on M or anything at all? Does it mean
well,
we have this sphere?
So I am assuming that it admits an ideal tetrahedral decomposition. So that implies that it has some boundary.
Okay.
So, okay. So just an ideal tetrahedral decomposition that has these special properties. So there is a boundary out there. Yeah, actually, you can show something stronger than this too. Not only will this be hyperbolic, you can determine that the boundary components will all be tori in this case as well, even if it admits an angle structure. So it's quite strong. Okay, other questions? All right, so let me see. So where was I? Okay, so we've got this essential sphere, disk, torus, or annulus. We can take S to be in normal form. Okay, and that is just by our favorite three-manifold topology, innermost disk, outermost arc type argument. It's kind of fun. Remember, that was the exercise everybody has to do once in their life, if you haven't. Okay, so S is in normal form now. I did that once in my life. I can assume it. Some of you have to keep working on it. But okay, so because it's in normal form, I can assign it a combinatorial area. As combinatorial area okay, here we go. So this is fun. So now Gauss-Bonnet. Implies that my combinatorial area is negative 2 pi times the Euler characteristic of S. So if S is a disk or a sphere, then the Euler characteristic is strictly positive, which implies my area is strictly negative. And what's the contradiction? Contradiction to the lemma. But area of S is the sum of these areas of the DIs, and these are all positive, so contradiction. Okay, so no disks or spheres. I was hoping I could fit the whole proof into that board. I don't think it's going to happen. Okay, now I have to think about my board work. I'm not going to use the third board. I am going to erase E. I kind of want to keep a lot of this. I want that. I want the normal form. I want the definition of angle structure. I want the definition of combinatorial area. I need my lemma. I don't need the proof of my lemma. I don't really need that example. So I'm erasing one of these two words. Okay, so we're going to put it here. And then I'll erase everything in just a few more minutes. Okay. So continuing on, if S is a torus, then we know that the area is negative 2 pi chi of S, which is 0. So this tells me that my surface is built out of disks that all have area 0, which means they are either vertex triangles or boundary bigons. Now, because this is a torus, it doesn't meet the boundary, so they're not boundary bigons. Each DI is a vertex triangle. Okay, because S has no boundary. Okay, well, if each normal disk is a vertex triangle, that means each of these is parallel into the boundary. And you can show then that S is parallel into the boundary of M. And that means that it is not essential. Remember, to be essential, it can't be boundary parallel. Okay, so that would be a contradiction. Okay, so we've ruled out disks, spheres, and tori. The only thing left is an annulus. So if, sorry, bigger S is an annulus, then again, so its area is 0, but now this does have boundary, and annulus meets the boundary of M, so there has to be a boundary bigone. So same argument tells me that all of my DIs are vertex triangles or boundary bigones. There's got to be at least one boundary bigone. Okay, so I've still got a picture of a boundary bigone. There it is. This boundary bigone glues to another, either a boundary bigone or a vertex triangle. The gluing is across faces of the tetrahedra. So there's no way this can glue to a vertex triangle. The boundary bigone has to glue to a boundary bigone. Okay, so this glues to a boundary bigone on both sides. So we have boundary bigone, boundary bigone. This glues to a boundary bigone, which glues to a boundary bigone, and so on and so on. You get everything here in sight is a boundary bigone, and moreover, so this has to close up, so S is made up of only boundary bigones. S is made up of boundary bigones. Boundary bigones. Okay, what's the problem here? There's a contradiction that's hiding in sight. Do you see it? There is a compressing disk. All these boundary bigones, the boundary bigone separates off exactly one edge. When you put all of them in a row, they are separating off the same edge. A compressing disk that's perpendicular to that edge. There's a compressing disk that's perpendicular to that edge. Okay, so S is made up of boundary bigones, and then this implies, well, I'll draw the picture from the top down. It looks something like this. Here's a boundary bigone. Here's a boundary bigone. Here's a boundary bigone, and so on and so on and so on, and then this is compressible. So they encircle an edge, and it's compressible. And that is a contradiction. Okay? All right, questions, comments? So there you go. So we have now an examples of manifolds that are hyperbolic. So anything that admits an angle structure.
So Jessica,
yeah.
You said it's hard to get an angle structure that's not the actual hyperbolic structure.
Oh, for me, it's hard to get an angle structure that's not the actual hyperbolic structure, yeah.
Can you take that hyperbolic structure and like deform it, like wiggle it a little bit, and it'll still be an angle structure?
Yes, you can take a hyperbolic structure and wiggle it a little bit to get an angle structure, yeah. That's why you know there are lots of them if you have one. Yeah, but in that case, though, you somehow still have the correct triangulation. And so you can find angle structures on the wrong triangulation also that will work. Okay, so I have 20 minutes left. I want to generalize this to families that are quite useful, which is the family of alternating links. Okay, so I guess I can't keep everything. I'll erase this board. Really tempted to use that third board. Yeah. Okay. Yeah, I'm just gonna have to start over and erase everything. It's okay. Just remember everything. That's fine, right? Okay, so this will take us back to something that I promised you from the first day. So an alternating link. This is a knot or link. We're going to be thinking of this in S3. There are generalizations, and most of this works. But anyway, so an alternating link, what this means is you have a diagram that is alternating, meaning if you start somewhere on your knot strand and you start walking, then you will see when crossings will be over and under in an alternating way, right? So here it's over, then under, then over, then under, then over, then under, and so on, over, under, until you get back to where you started with. So crossings alternate over, under. So that's the definition of an alternating link. We had a decomposition of the figure 8 knot, which is this one. I can't draw very many knots. Here's the figure 8 knot complement. We decomposed it into 2 ideal polyhedra on Tuesday. Everything that I did there generalizes immediately to all alternating knots. So this decomposition of the figure 8 knot from lecture 1 generalizes to a nice decomposition of any alternating link. Okay, so how did that work? So step 1 was, we have my link, yada, yada, that's alternating. Okay, we took a ball on the top and a ball on the bottom and we started expanding. The balls got decorated with information. First of all, the faces were the regions of the diagram. The edges came from crossing arcs. And then we pulled away the remnants of the knots on the top and the bottom to get ideal vertices. So that works. All those 3 steps work in full generality for any alternating knot or link. So let me make this a theorem. I need a little more space. So let L be an alternating link. So knot is 1 component, link can have more than 1 component. This works for both. Then S3 minus L can be obtained by gluing two ideal polyhedra that satisfy the following. Okay, first of all, so how do you get the polyhedra? Well, you take these balls, and in the case of an alternating knot, this is special to alternating knots, you just label the balls with the diagram graph. Okay. So polyhedra are obtained by labeling the boundary of the balls with the diagram graph. So, and then also, so we got this with the figure 8 knot. One of the balls we had our head inside and one of the balls we had our head outside, and so that's still going to be true. So one ball head is inside, one is out. Okay, it's not going to matter for the combinatorics, but it's useful to know sometimes where your head is. Okay. Second property. The ideal edges of this polyhedron glue to be the crossing arcs. So, right, so what's a crossing arc? It's this arc that runs between crossings. And when we did our decomposition, we drew each one 4 times. But these are all isotopic to just this single vertical edge like so. Okay, ideal edges glue to the crossing arcs, and each edge class contains 4 vertices. Or sorry, 4 edges. So they are exactly these 4 edges we drew onto the diagram, and then we started playing with which way they go, if your head is on this side or on that side of the board. Okay, number 3, the faces. So these faces come from the regions in the complement of the diagram graph, and they can be checkerboard colored. So I didn't point this out. You spell colored with a U in Australia, by the way. So anytime you have a 4-valent planar graph, you can checkerboard color the regions. I didn't point this out before, but it's useful for the gluing. So it turns out that, so you get these white faces and shaded faces. If you trace back through the diagrams that we created, you can see exactly how these glue. So the face on one polyhedron is identified to its corresponding face. So it's glued to the same face on the other polyhedron, but with a rotation. Rotation. And this, if you're in a white face, then you rotate by one edge clockwise. And if you are in a shaded face, then you rotate by one edge counterclockwise. Okay, so I've already kind of sketched how to do that, at least for the one example. And so a nice exercise is to see that this really works for all examples. So the gluing, what do I mean by this rotation? So in a shaded face, if you are on this edge gets glued to this next guy over. One edge, it would be glued to here in the counterclockwise direction. So this is glued to this one is glued to that one, and so on. If you're on a white face, you get glued in this way. So these little edges of gluing are always parallel across an edge. So there's one there, there's one there. I screwed up. This one. There we go. Okay. Okay, Thurston noticed this for the figure 8 knot, and he compared it to a gear rotation. So this is sometimes called the gear rotation gluing for alternating knots. Okay, so we don't have ideal tetrahedra anymore. We have ideal polyhedra, but we can immediately generalize this idea of an angle structure to an ideal polyhedron. Oh, I should say too, one thing that I'm not doing, the last step we did for the figure 8 knot complement is that we collapsed the bigons. Keep the bigons. We're gonna leave the bigons around. So this is not hyperbolic at all, but it's going to be good enough. Okay. An angled polyhedral structure on a 3-manifold is a decomposition of M into ideal polyhedra along with a collection of interior angles, so one for each edge, and a collection of dihedral angles one for each edge satisfying a lot of the same properties. So first of all, the angles lie in 0 to pi. I don't need this first property because there's no such thing as opposite edges if I have a more general polyhedron. Okay, but the angles have to be in 0 pi. 2, the generalization of this property is that every normal disk has non-negative combinatorial area. Maybe this is stronger than that anyway. Interior angles around an edge sum to pi. Okay, so I actually am realizing I didn't tell you what the combinatorial area is, and I erased that. I think I was careful. Its combinatorial area is just defined by, again, if you have a normal disk. So a normal disk is still okay. This is for any polyhedron. You truncate the polyhedron, you make sure that it doesn't do these bad things, and then it's normal. So you look at all of the edges it meets that have an angle, and you add up, you get the same formula that we had before for the combinatorial area. So combinatorial area makes sense anytime you have a polyhedral decomposition and anytime you assign dihedral angles to your thing, okay? So provided each normal disk has non-negative combinatorial area, then you get one of these structures. So an example of an angled polyhedral structure is an angled structure, is this guy. Right, angle structure. But an angle structure is only good for tetrahedra. Whereas angle polyhedra are much more broad. Another example is given by alternating knots. So this, I think this is due to Mark Lackenby. It's definitely in his paper from 2000. It could be Aitchison and Rubinstein, I think, were also looking at these sorts of things, but I don't think they were putting angles on things. So nobody is shaking their head as if they know. So we'll call it Lackenby. Okay, so here we go. So we're going to assign a dihedral angle pi over 2 to each edge of this decomposition right there. Okay, and then I claim that this is an angled polyhedral structure. This is an angled polyhedral structure. Okay, so how do you see this? Okay, so first of all, this is not true. Yada-da. I need let L be a prime alternating diagram. So I need to tell you what prime means. So instead of the proof, let's do that first. prime diagram. Any simple closed curve meeting the diagram transversely exactly twice bounds a disk with no crossings. So that's the definition in words. This is actually a definition that works better in picture. Let me draw a knot. I can't draw very many. So here's a knot. Okay, that is not prime. Why? Because there is a simple closed curve meeting the knot transversely exactly twice, 1, 2. On this side it bounds a disk with crossings. On this side it bounds a disk with crossings. So that's not prime. Okay, so we need, this is a connect sum. So we don't want connect sums, we want simplified things. So to get a prime diagram out of this, you would erase all these crossings and just connect this by a blob with no crossings. That would be prime. So that would be okay.
Well, not split.
Yeah, we're also non-split. A non-split diagram is a connected diagram. Yeah. Okay. Should I throw in some more adjectives? Am I missing any? I think this is okay. All right. Yeah. Okay. So all right. So let me just tell you in words what goes through. You get this combinatorial area still. So okay. So this is an angled polyhedral structure. It's easy to see. Number one, the angles are pi halves. They lie in 0 to pi. It's easy to see interior angles around an edge sum to 2 pi. Sorry, 2 pi. It's easy to see 2, if I get it correct, because there are exactly 4 edges in an edge class. All of them have angle pi halves. Okay, so sorry, I had that written down wrong. The interior angles around, this is an edge in an edge class, all have to sum to give me 2 pi. This is the analog of number 3 over there. So because I've got exactly 4 edges, all labeled pi halves, they sum to 2 pi. So that's easy. So the trick is showing that normal disks have non-negative combinatorial area. And for that, you use the fact that this is prime. Okay, so that maybe let's leave that as an exercise. Proof, exercise. Everything gets to be an exercise now that we're out of time. Exercise. I can't spell I don't know. Okay. Okay, what else? Gauss-Bonnet is still true. The proof is identical as it was in the case you had tetrahedra. And then this theorem so Gauss-Bonnet, a normal surface S in an angled polyhedral decomposition. Still satisfies the Gauss-Bonnet formula. So then the theorem is that if M admits an angled polyhedral decomposition, you don't get something quite as strong as hyperbolic. Then M is irreducible, boundary irreducible. So I think this is Lakenby actually. Okay, and the proof for this is the same. So we have Gauss-Bonnet, meaning that the area, combinatorial area is basically the Euler characteristic. If it's got an essential sphere or an essential disk, then it has a surface with negative combinatorial area, contradiction to this statement, this second thing right here. Okay, so that's easy. So corollary is that these prime connected alternating diagrams, the complement of those are irreducible, boundary irreducible, alternating knots, irreducible, boundary irreducible. Okay, and then I should put up, so we are out of time. So let me just say though, you have to take a little bit more care to look for essential tori and annuli. And Manasco did this without using combinatorial area, but you can do it with combinatorial area. So there's the theorem due to Manasco is that for these prime alternating connected knots, S3 minus L admits an essential annulus if and only if it's a 2Q torus link. Okay, 2Q torus link. And S3 minus L never contains an essential torus. So that means that everything except 2Q torus links are hyperbolic for these alternating links. Okay, so I am out of time, so let me stop there. Thank you.